Geometric series are a very specific type of series. And this type of series has a very specific rule as to how to find out if it's converging or diverging. So let's look at what the geometric series looks like first. This is the general form. If you've heard of geometric series or geometric sequences before, the idea is that you're multiplying by the same number each time. If you watch the series intro video, we had the one with the bouncing ball where the bounce height was 3/4 of the previous height each time. So we were multiplying by 3/4, multiplying by 3/4, multiplying by 3/4. Or the one where we go 1/2, 1/4, 1/8, 1/16, we're multiplying by 1/2 each time. So this is what a geometric series looks like. It has that form. Now it's really simple to tell if it converges or diverges. If the absolute value of r is less than 1, it converges. Another way to say that is r is between -1 and +1. So it can be -1/2, +1/2, +3/5, -4/5. Anything between -1 and +1 converges. Now that's the r. It's important you watch the r. Now if the r is 1 or bigger, if the absolute value of r is 1 or bigger, then it diverges. So all you have to do to determine if a geometric series converges or diverges is identify the r and figure out if it's less than or equal to 1 in an absolute sense. Geometric series are also one of the few series that we can easily find the sum of, and that's with this formula. So the sum of a convergent series is a over 1 minus r. Now it's important that I worded it that way, the sum of a convergent series. This formula does not work if the series diverges. If the series diverges, your answer should just be infinity or negative infinity if they mention the sum. But the sum of a convergent series can be found by using a over 1 minus r. So only use that formula if you actually know it converges. Well, let's look at an example. Okay, here we have 2 times 1/2 to the n. So this is my a, and this is my r. So my r is 1/2. Since that's less than 1, I immediately know that it does converge. And since it converges, I can find the sum. I just put in a over 1 minus r, which is what you see here, 2 over 1 minus 1/2, and it gives me the sum of 4. So if I add up all the terms from that sequence, 2 times 1/2 to the n, to infinity, I get 4. Okay, now just so you know, geometric series can disguise themselves. Sometimes they don't look exactly like that a times r to the n format. So for example here, this really can be rewritten as 1/2 to the n, because 1/2 to the n is really just 1 to the n over 2 to the n, and 1 to any power is just 1, so that just loops us right back around to where we started, which is 1 over 2 to the n. So this is the more normal form, or the more standard form for a geometric series. But it looks like 1 over 2 to the n in the original, but this is equivalent. It's the same thing. Now this second one's a little trickier. Some people are tempted to rewrite that as 3/2 to the n, but that's not true. 3 is not being raised to the n, and it does change 3 when you raise it to the n. So the first thing you should do in this case is pull the 3 out front. Then you can rewrite it as 3 times 1/2 to the n. So your a would be 3 and your r would be 1/2. And both of these would be examples of ones that converge. Okay, the other tricky thing they'll try to do is the formula a over 1 minus r, so this just has to do with the sum, what I'm about to explain, only works when the first term is a times r to the 0. So just to pull up an example, this is one like we just wrote, 3 1/2 to the n. So my first term I plug in is 0, so that does work just fine. I have a times r to the 0, no problem. But sometimes they'll disguise that, and they might actually have something like this, where it starts at n equals 1, but they'll rewrite the exponent as n minus 1. So that may look like it's not going to work out, but if you plug 1 in right here, 1 minus 1 is 0. So that's still okay. You still get a times r to the 0. But if it doesn't start like that, if you have something like this, then you're going to have to adjust your sum. So let me show you how you have to do that. Let's just go with a simple one where it's 1 times 1/2 to the n, and we'll compare what it looks like when you start at 0 versus when you start at 1. So when we start at 0, the top one, we get 1/2 to the 0, which is 1, plus 1/2 to the first, plus 1/2 squared, plus 1/2 cubed, and so on. So that's 1 plus 1/2 plus 1/4 plus 1/8, and so on. Now if we start at 1, we start with 1/2 to the first, plus 1/2 squared, plus 1/2 cubed, and so on. So we get 1/2 plus 1/4 plus 1/8. So if you notice, from 1/2 on, these are identical. But the one that starts at 0 has an extra term. Because if you think about the geometric series in general, its terms are a times r to the 0 plus a times r to the first plus a times r squared plus a times r cubed, and so on. So what happens when we started at 1 is we miss this first term. So we can still use a over 1 minus r if we then subtract a times r to the 0, which, if you notice, is just a. But we've eliminated that first term. So in this example up here, we can still do a over 1 minus r. But if we're using this one that starts at 1, we have to account for the fact that we're missing the 1, so we have to subtract 1 from our answer. So we end up with 2 minus 1, which is 1. And then if you have one that starts at 2, you're going to have to subtract 2 terms. So if you have this, then you're going to be missing your AR to the 0 and the AR to the 1. So in that case, you have to do a over 1 minus r minus AR to the 0 minus AR to the first.